Well, good morning, everyone. This is Hal Green with Geophysical Insights in Houston. I manage marketing for Geophysical Insights, and I'm delighted to welcome you all to our continuing webinar series on machine learning for seismic interpretation. In just a moment, Rocky Roden and Alvaro Chaveste will present a new machine learning methodology for reservoir characterization that can be done in a fraction of the time and cost compared to traditional seismic inversion methods. Now, we understand that this is a substantial claim, and we're prepared, my colleagues are prepared to back it up to show how the methodology works in slides and in live software supported by case studies. Many of you know Rocky Roden, our first speaker, who has attended our prior webinars. It's a pleasure to have him back with us on our series. Rocky started Rocky Ridge Resources in 2003 and worked with several oil companies on technical and prospect evaluation. In addition to being an oil finder of 47 years in the industry, gaining extensive knowledge of modern geoscience technical approaches, Rocky has a deep technical background. As chief geophysicist, now retired, and director of applied technology for Repsol YPF, his roles included advising corporate officers, geoscientists, and managers on interpretation, strategy, and technical analysis for exploration and development in offices internationally. Rocky has also led technical and economic evaluations of the Gulf of Mexico, lease sales, farm outs worldwide, and bid rounds in South America, Europe, and the Far East. His previous work experience includes exploration and development in Maxis Energy, Pogo Producing, Deca Survey, and Texaco. Rocky is a member of the SEG, AAPG, Houston Geological Society, Geophysical Society of Houston, the EAGE, and CIPES. He is also past chairman of the Leading Edge editorial board, and he holds a BS in Oceanographic Technology Geology from Lamar University and a Master's of Science in Geological and Geophysical Oceanography from Texas A&M. We are also pleased to hear Alvaro Chaveste, who is relatively new with Geophysical Insights, joining the firm as a senior consultant in July of 2022. Alvaro's background makes him ideally positioned to address today's topic, along with Rocky. He has deep experience in seismic data acquisition, rock physics, anisotropy, data processing, quantitative interpretation, and machine learning. His previous roles include Manager of Advanced Reservoir Geophysics Group at Core Laboratories, Director of Interpretation at Geokinetics, and Senior Geophysical Advisor in the Technology Group at Hess. Currently, Alvaro is leading the development of the geoscience technologies featured in today's webinar, and he is also consulting with many of our clients. He holds a Bachelor's of Science in Geophysics from Montana Technological University and has conducted graduate studies at the University of Houston. Mr. Chaveste is also from Mexico and fluent in Spanish, an important skill for our location and some of our clients. And now I'm delighted to turn it over to our presenters. Rocky?
Thank you, Hal. Appreciate it. It's a pleasure to be here this morning for you. Alvaro's going to draw this PowerPoint as I give the first few slides, and then he's going to really get into the meat of this. So you can go, obviously, as Hal indicated, our presentation is entitled The Advantages of Machine Learning over Seismic Inversion for Reservoir Characterization. And we're going to give you some of the reasons for this and show you what we're talking about, how this works. So Alvaro, why don't you go to the first slide? So what we're going to do, I'm going to give a few slides here at the very beginning on the state of inversion for reservoir characterization in our industry. I've got a lot of experience in this, and I want to share that with you. And then Alvaro is going to get into the meat of the presentation, where the machine learning reservoir characterization is going to give you a proof of concept with some models. And then we're going to actually use a real setting with lithological identification in the Niobrara, which is a resource play in the United States. So why don't you go to the next one there, Alvaro? This is a summary. We're going to put this right up front of what we're going to talk about. And of course, what the machine learning approach that we're talking about is self-organizing maps using seismic data. And it's not based on inversion and does not require a seismic data to fit a model. We use a series of multiple attributes that looks at the data and identifies the natural patterns and clusters in the data. And these neurons, these sets of neurons, have the properties of inverted data. They're going to be correlated with the reservoir characterization properties that we're looking for. And of course, the lithofacies from the wells and the petrophysical evaluation, we need to understand that too, because once we run these unsupervised machine learning approach called self-organizing maps, we're going to correlate that with the lithofacies from the wells from the petrophysical examination or the evaluation. And so it's the sum to lithofacies correlation, which is where we see the results statistically on the reservoir properties and how they relate in our data to the seismic data versus the well data. So with that, why don't you go to the next one, Alvaro? Now, reservoir characterization, as we all know, is determining the physical properties of reservoir and changes in their distribution throughout the reservoir, like porosity, permeability, fluid saturation. And of course, what we try to do is derive these properties from our seismic data. Let's go to the next one. And typical seismic inversion, the seismic inversion process, which we've known for years, converts seismic reflection data, which is an interface property. In other words, the amplitudes that we see in our normal seismic data, into a model of subsurface acoustic impedance layers. So we're converting these interface properties into acoustic impedance layer properties. And depending on the type of inversion that you're using, these acoustic impedance layers can be transformed into reservoir properties, like porosity, VPVS, all these sorts of reservoir properties that we're looking for in the inversion process. Now, I can tell you that over more than the last 23 years, I've been evaluating prospects well over 400, probably 450 around the world, from national oil companies, major oil companies, large, medium, and small independents. And I help evaluate these prospects, and we risk these prospects. And more importantly, I get to see the actual results ultimately. And many of these prospects that I've looked at have inversion applied to them. Some sort of inversion has been employed. In fact, what you're looking at here on the left is a set of inversion types. And I've seen most of those many times, and I've seen the results from the wells that have been drilled on these inversions. And of course, when you're looking for reservoir properties, you have to be determining the absolute impedance. The relative acoustic impedance doesn't mean anything because you're trying to convert these to reservoir properties. And I can tell you, when you go from exploration into a large degree into exploitation, you absolutely have to have a lot of well control, and you have to have a lot of good quality well control information. That's why in exploration and exploitation, the answers you get in inversion are very non-unique. And it's very difficult to get very accurate answers when you don't have the well control, because in conventional inversion, especially deterministic inversion, you have to have a certain amount of well control to drive the answers. Now, the only potential exception to this is when you get to stochastic, the geostatistical and Bayesian inversions, these sorts of things. Well, right up front, they require a lot of well control and a lot of good quality well control. So you need to keep this in mind when you're thinking about inversion, and be very, very careful when you're in the exploration and exploitation phase of a well, and the non-uniqueness of an answer, regardless of the type of inversion that you're using. Okay, I'll go to the next one. And of course, the requirements for a typical deterministic acoustic impedance inversion is you have the wavelet estimation, which is not trivial by any means. A determination of the low frequency trend, again, not trivial at all. You need to have high quality seismic data to get the best answers. And you have to obviously have well control for the reservoir properties, because that drives the inversion process. And it's quite computer intensive. And depending on what type of inversion, it can be extremely expensive and potentially take a long time to compute. So what are the issues? Well, first of all, you get a non-unique solution. The accuracy is directly related to the amount and quality of the well control. It's sensitive to nonlinearities, uncertainties, and assumptions employed. That's one of the biggest things that's missing, I think, in our industry that a lot of people don't realize. A lot of our geology is not linear. In fact, I would argue that most of it is not linear. And the assumptions you make in the inversion process can make that quite difficult to get the right answers. Most inversions are inappropriate for detailed quantitative interpretation for thin beds. When you get below tuning, it starts to be, when you're looking at amplitude data and you're getting below tuning, the time separation doesn't change anymore once you get to the tuning thickness. The only thing that changes is the amplitude, and the inversions are absolutely start to be inaccurate when you get to that stage of the game. And inversions assume that all the information related to reservoir properties is incorporated in the amplitude data alone. Why? Why are we only using amplitude data? Well, the application of 5 to 10 seismic attributes in a machine learning process like self-organizing maps, it decreases the non-uniqueness of the solution and addresses thin beds, as opposed to employing amplitude data alone for inversion. There are a lot of different phenomena that are occurring below tuning when you look at different attributes that are not amplitude. Any frequency-related attribute has some sort of phenomena. There's a thing called frequency tuning occurs below tuning. So anyway, these are incorporated in these machine learning approaches. So remember, no, it's fine. We'll go to the next one. So remember that the inversion for reservoir properties, if you're trying to get reservoir properties from a quantitative standpoint, requires lots of high quality well control to compute reasonable results. Obviously, it's time consuming, quite expensive. But if you're using the self-organizing math machine learning, remember this is an unsupervised machine learning approach. It doesn't care how much well control you have. When you run this, you're going to get the same answer whether you have no wells or 100 wells. What you do is after you run this, the results are correlated afterward with the well control to derive the reservoir properties. And I just want to leave one last word here is in the last recent image conference in Houston, Partha Roth of Exxon gave a talk on full waveform inversion, the ultimate form of inversion in our industry. And he made a statement. They said, even if with the most advanced elastic full waveform inversion and all the computer power and high performance computing in the world at your disposal, at the end of the day, you still do not cannot break out definitively between wells the density and velocity and the acoustic impedance that you've broken out. That's the non-uniqueness of inversion, and you're always going to have to deal with that. So with that, I'm going to hand this over to Alvaro.
So yeah, so Rocky mentioned some of the or made a comparison of or mentioned some of the differences between doing reservoir characterization the conventional way using well cell inversion, and then mentioned some of the differences with reservoir characterization using machine learning. In this case, self-organized maps. What I'm going to be doing now is that I'm going to show the proof of concept, which is also the methodology or the steps that we're following to come up with a result. So I'm going to do that with a synthetic data set, and then after that we're going to show results with real data and illustrate the results in 3D viewer, the viewer of Paradise from Geophysical Insights. So I'm going to start by showing the data processing. In this part, in the data processing, I'm going to show how we created the synthetic. Then we're going to see how we're going to define lithofacies, doing the self-organized map of petrophysical properties. We're going to do then the self-organized map of seismic data. And then finally, we are going to correlate, or we're going to cross-reference the lithofacies that we created with the sum from the seismic to come up with the reservoir characterization results. So as far as the data that we're using goes, as I was saying, this is synthetic data. And the way that it was created is that we took a well. It's a real well. It's from South Africa. And that well has a petrophysical evaluation. It has shale volume, porosity, water saturation, and we copied the well in 31 lines and 41 cross lines, creating a total of 1,271 traces. Effectively, each trace is a well. So we're going to have a well in here, which is going to have a shale volume, a log, a porosity log, and a water saturation log. And then in the middle sand, in the thick pay sand, we modeled, or we created a block sand that we're going to, or 3 different block sands, which are going to be the target of the proof of concept. So you can see here the time slice at 3.107 seconds, and you can see the 3 target sands. One, they are gas sands. One is 16% porosity, 18% porosity, 20% porosity, and here you can see the inline, which would be down in here. You can see the the sand that we have introduced here to do the proof of concept. Once we have created our volumes of petrophysical properties, we use a rock physics model to compute the seismic data. This will be the seismic data that we're going to be using in our study. This is inline 7. You can see here the anomaly associated to the gas sand, and we used a wavelet of 5, 10, 50, 75 hertz, which has a resolution slightly better than that required to identify the zone of interest. Okay, so this would be as far as the seismic goes. We also need well logs from which we can do the lithofacies. And as I was mentioning, we are using a cube that is very much every trace represents a well with three petrophysical logs. So what we did is that we extracted the logs from the cube. We extracted 6 logs, or sorry, 6 wells. Wells 1, 2, and 3 are in non-pay or in the shaly part of the synthetic. Right here you can see well 3. You can see that it has high B shale, low porosity, high water saturation. This is a non-pay well. And also I show here well 6, which would be here, which has high porosity, low B shale, and low water saturation. This would be a pay well. So this creates our seismic and our well log data. Now, in the next step, we're going to create the lithofacies, just doing the self-organized map of the petrophysical properties. So I start here by showing the petrophysical properties. I have a B shale, porosity, water saturation. Right here, these are the three sands that I just mentioned. You can see that these are low B shale, high porosity, 16, 18, and 20% porosity, and low water saturation. So these are the pay sands that I know that exist there. So the first thing that we're going to do is that we're going to do some in the petrophysical evaluation, and we're going to get 4 neurons. Now, in the lithofacies, we're going to rename, or we're going to name the same neurons or lithofacies. So this neuron, or the contents of this neuron, would be a lithofacies. This would be another lithofacies. So what I can see here is that these red points corresponding to this neuron, I can call a pay sand, again, because it's low B shale, high porosity, low water saturation. This in here, the gray points, I can call a shale, because it's high B shale, low porosity, high water saturation. Another way of evaluating this petrophysical evaluation and the phases is by doing PDFs of each of the neurons or each of the lithophases. So here I have the red points. This would be the PDF of the red points. Again, I would have relatively high porosity, approaching, in this case, 18%, 18 to 20%. I would have low water saturation, low B shale. So I'm going to call this the gas sand, these points. Now here, this is the PDF of these gray points. You can see that porosity is lower, B shale is larger, and the water saturation is basically, very high, very close to 1 or 1. So I'm going to call this shale. So these points are called shale. And similarly, I have these other two phases that I'm going to call wet sand here in yellow, and then sandy shale here in brown. So that's the way that we create the lithophases. Let's now go to the self-organized map of the seismic data. And to illustrate this, I would like to go back again to a model. This is the same well, but in this case, I didn't create a blocky sand. I left it the way that it's originally acquired, and modified the porosity in the interval that we are evaluating. And here, so I have a sand in which I change the porosity. I create a stack using the same rock physics model that I mentioned before, and then I do a recursive inversion. Parallel to the recursive inversion, this is what you would obtain if you do the recursive inversion of a seismic volume. Parallel to that, we created an 8x8 self-organized map, and then here I highlighted some of the neurons here and obtained the same, the same body, the same porosity sand that is changing porosity, and it goes. You can see that it goes slightly further than the seismic, and you see here another two bodies. But we're going to come back to this in just a minute. Okay, so some of the properties of the SOMs is that they map band limited reflectivity to broadband interval properties. So you can see here we're going from reflectivity to interval properties, and it relaxes the data processing through amplitude requirement. That is, we still need well-processed data, but it doesn't have to be as demanding. The processing does not have to be as demanding as when we're trying to do inversion. And I'm going to illustrate these 2 points with these other comments comparing these two images. And we see that the sums show the equivalent of wavelet removal. That is, we do not have side lobes. Again, you can see here that we don't have the side lobes. We are mapping, very close to what we have here in the porosity. You can see here in the recursive inversion, there's still side lobes right here. This blue data are part of the side lobes. Also here, you don't see these two layers as well defined. These two layers are actually also sands in which we're changing the porosity, and that is because in here the side lobes were eliminated. Another point is that some neurons can be selected to highlight or evaluate specific conditions, and that's what I illustrate here. I am selecting this neuron to highlight, in this case, the sands in which porosity is changing. And then finally, The sums show 1 neuron per sample. That is, we're going to have several neurons within a wavelet's limit of resolution. That is, we're going to have interpretable data under the limit of resolution, with the wavelet's limit of resolution. And I would like to illustrate this point further with this image, which is this same stacking here, and then superimposing this sum here. You can see in this zoning here we have a peak. It's very difficult to say what's inside the peak. When we do the sum, we get different neurons within the sum. Within the peak. So we're getting interpretable data in this peak. The same down in here, you can see that we have a peak, and when we do the sum, we get additional information within that peak, and also here in this small stringer of data. So that is the sum. So now we have computed the lithofacies using the self-organized maps of petrophysical properties. We have computed the self-organized map of the seismic data, and now we're going to take the lithofacies, the sum, and we're going to do the correlation. And what do I want to obtain with the correlation? What we want to do is, well, first of all, I have here the self-organized maps. I have here the neuron topology. In this case, this is a 12 by 12 neurons. And what I would like to do is to have a color map or to identify or to mark by colors each of these neurons such that each neuron represents a geological condition or a lithofacies condition. So that's what I'm doing here. When I do the sum to lithofacies correlation, what I obtain is that this neuron here is going to correspond to a 20% porosity gas sand. This neuron here, right here too, is going to correspond to an 18% porosity gas sand, and this is going to correspond to a 16% porosity gas sand. And that's what we get when, when I select these 3 neurons from the topological map. I can identify the 3 sands within the synthetic data set that I created. So these 3 are embedded in this cube here. Additionally to that, I am also going to obtain an estimate of probability, and I'm going to annotate that probability as a tone in the color. That is, for example, you can see here this gray corresponds to shale. It is dark gray, meaning that the probability of that neuron being shale is 1, and then in here it's lighter, and this probability of this neuron being shale is 40%. So I'm obtaining both. I'm calling this the winning lithofacies, and then also the probability. Okay, so that concludes the proof of concept. Let's go now to the real data. Okay, and as Rocky mentioned, we're going to show how the method works in the Niobrara formation. And the objective here is to identify lithology in the Niobrara. For this analysis, we did it from the top Niobrara to the top caudal formations. We have multi-mineral petrophysical evaluation in 5 of the wells. Sorry, this slide goes off by itself. And we have 100 square miles of seismic data. Okay, so I'm going to take the 5 wells that are used to estimate the four lithofacies, and or I'm going to use the 5 wells to estimate four lithofacies, and we see that the wells have 2 fluids, in this case hydrocarbon and water, and 4 different rock types, being calcite, dolomite, silt, and clay. So when I take the petrophysical evaluation and do the sum of those, I get the following phases or the following neurons. This would be the content inside the neurons. You can see, or I can see here, that the phases 1 has a high content of calcite, so I'm going to call this phases calcite. Phases 2 has high content of dolomite, so I'm going to call this phases dolomite. Phases 3 has about the same content of dolomite and calcite, so I'm going to call this, let's call it generic carbonate or carbonate. And then phases 4 has a higher content of clay. Okay, so the next step, so I have created here my lithofacies. The next step is to verify these lithofacies with the well logs with the petrophysical evaluation, just as a corroboration that we have been doing things correctly. Before doing that, I would like to refer you to this image. We're going to be working with this image in the next slides. And this is the well that we have been working with. This in here would be the sum of the seismic that was previously created. These here are the lithofacies that we just created. And this here is the trough of the seismic data. Now here, what I note in here, or what I would like you to see, is that within this trough, we have this is still well data, but we have in here embedded here. We have two layers of clay, and then we show here also dolomite. Down in here we see calcite. What I'm trying to say is that we have a lot of events within one trough of the seismic data. Okay, that being said, let's now go to the verification of the lithofacies to the petrophysical evaluation logs. And to do that, what I do here is we have here the neurons from the seismic. Here I have the calcite log from the petrophysical evaluation, and here I have the phases that we just computed. And I have in here a baseline of 0.55, 55%. This will be this baseline. And I see that all the points with calcite higher than 55% match the phases here and here. I do the same with the dolomite. The dolomite, in this case, the baseline is 45%. And I can see that, this matches very well here from the well logs and the phases. And the same with the clay. So I think that that gives confidence that the sum from the well logs did what it was supposed to do. So now what I'm going to do is that I'm going to do the correlation. I am going to correlate or to cross-reference the phases with the neurons and obtain a lithofacies topology displays or maps. So what this is saying is that when I take these neurons and I select this neuron, I'm going to have a probability of 57% of that neuron being in this case dolomite. This would be calcite, this would be carbonate, and these two would be shale. And also display as a tone of the color of the neuron the probability of each one being the lithology or lithofacies of this particular color. Okay, so let's now look at the real data, the seismic. This is the seismic in one of the lines, and this is the well. The log that you're seeing here is for reference, and it is the same as you're seeing here. These are the neurons, and then in here I have the self-organized maps before the sum to log correlation or the sum to phases correlation, and then in here I have the sum to phases correlation. And I want to compare this with the well log. And what I see here is right here is this again, this log is these neurons from the log. You can see here we have carbonate in here. We have here two stringers of shale. Right here is one, right here is the other one, embedded in dolomite. Right here is the dolomite. We have here carbonate, which would be this brown carbonate, some dolomite, another carbonate, and then we'll get into the calcite here. Then here we get again the carbonate, what we're calling carbonate, the dolomite. We are missing this stringer of clay in here. We have again carbonate topping the calcite, and then the calcite here. So I think that this is a very good correlation. And importantly, or you can see here, this is a trough. And within this trough, we are getting all this information from the sum. And you can see this and the next image, you can see a verification of this. So take a look at this, and then these are the same. This is the same, but in the seismic, you can see the amount of information that we're getting in the trough. I think that's very good. Okay, now what we are seeing here is the same, the same data, but in this case in time slice. Right here at 1.54 seconds is the seismic. This right here is the self-organized map, and this here is the time slice. And from the time slice, we see here, sorry, the the sum to lithofacies correlation. And here you can see this has a high probability or a higher probability of being dolomite, the same as this, but it's more probable that this is dolomite because this is darker green than this green. The same in here, this is calcite, but the probability is higher that this is calcite because it's dark, and this is also calcite because this is darker yellow than this yellow down in here. So we're seeing here not only the lithology or the lithofacies, but also a measure of the probability of that particular location being that lithofacies. And I would like to take over or do a little bit more on the on probability and on the lithofacies. And for that, I would like to show this. This is a zoom of what we saw before. This here is clay. This again is clay in here, and notice how this is broken. And in this area, I would expect that this would be blanket clay, not cut off gray like this. So what I'm going to do is I'm going to take a closer look at this, and here I start by looking at the topology, the lithofacies topology, and then noting the probability. So here it's difficult to see, but there's actually two colors in here. This here that follows, that continues with the clay is neuron 14, has a 46% probability of being dolomite, and this 15, which is over here, has a 77% probability of being dolomite. Now, what I'm going to do is that I'm going to do a similar map, but considering only the probability of clay. When I do that, I can see that neuron 14 as well has 46% probability of being clay. So the dolomite and the clay have the same probability. In here, the dolomite was chosen. I guess it was the order in which it was computed, but these two have the same probability. And to illustrate this, I'm going to jump now to show you the image in 3D viewer. Just a minute, let me see. Okay, so here we have the same image that we were seeing, and what we had mentioned here is that what we had mentioned here is that neuron 14 and neuron 7 had the same probability of being clay. So let's see here. Oh, sorry, I got the wrong one here. Should be this one. Okay, and as I was saying, let me look here the full, and I said that 14 and 7 have the same probability of being clay. When I look at this, you can see that they are continuous. That is, they are the same probability, and they are going to, it's basically the same formation. Now I can see the, the clay continuously. Now we also mentioned that 5 was also, we said 5, 6, 7, 5, 4, 5, 6, 7, and 14. So let's take a look. Right here is 4. And yeah, I mean, you can consider it part of the clay. In this case, I'm not going to include it because it's mostly, the very steeply dipping parts probably associated to faults. We mentioned 5. 5 appears to be mostly the lower shale that we were seeing, so I'm not going to consider it for now either. And 6 right here, it's still part of the same formation, but for now I'm just going to stick to 14 and 7 here. Okay, so now I want to see it, extensionally. To see it extensionally, first of all, I'm going to bring everything again. To see it extensionally, what I'm going to do is that I'm going to bring a horizon, and I am going to extract the, the neurons from the horizon. Right here, you can see the extent of, let me see, just a minute. Let me bring again here this, and so this is going to be the color selector for, for the horizon that I'm working here. I'm going to select 14 and 7, and this is what I would expect to see. It's more extension, but still I don't like the green and the purple colors, or the gray colors there. So what I'm going to do is that I'm going to bring now the color map of the probability of having clay. Okay, so that's the color map, the probability of being gray, and I'm going to select again 14 and 7, and now I get a more reliable, a more yeah, let's call it reliable display of the extent of the clay in the area. Okay, and so that's what I wanted to show you with the system here, and what I would like to to conclude or to mention, just to close, is keep in mind that we started with these two stringers, and keep in mind that these two stringers are already below the limit of resolution, and then even though they are under the limit of resolution, we were able to extend them through the whole project just by looking at the probability. So this I think shows the benefit of the method, of the technique. Okay, just to summarize, I'm going to repeat Rocky's summary and conclusions. We did the sum. We did the characterization doing the sum of the seismic data. It's not based on inversion. It does not require that seismic data fit a model. When we do inversion, we try that the seismic to fit one of the Sopritz approximations, Aken Richards or other approximation, and that's not easy task, and it's painful. We did multi-attribute data reduction through clustering analysis. We are taking, in this case, I think they are 9 attributes, and those 9 attributes are combined, are clustered to produce the sum. The sum results in neurons that groups that have the properties of inverted data. So basically, we did sum, and we got something that, at least when compared to a recursive inversion, I think the sum looks better. Then we did a lithofacies from well logs, petrophysical evaluation. We again did data reduction and came up with with the lithofacies that made more sense to evaluate when compared to the neurons. And then finally we did the sum to lithofacies correlation, in which result in a statistically reliable reservoir characterization, and the reservoir characterization results are obtained in a fraction of the time when compared to conventional characterization. And with that, I hope that you enjoyed it. I hope that it was illustrative, and the only thing left is to thank you and leave it open to questions.